Okay, so what I want to talk about now is the EPR incomplete there's got to be another incompleteness argument. Okay, the EPR incompleteness argument. Okay, so let's, I guess you have to kind of set the stage for some of this history. So historically, Heisenberg proposed matrix mechanics, then Schrödinger proposed wave mechanics, and quickly, Schrödinger actually is the one who wrote the paper showing that the two were the same, even though the description is, the mathematical description is very different. Heisenberg was using matrices, Schrödinger was solving smooth wave differential equations, but you could go back and forth. So they're identical ways of solving problems. However, each mathematical description kind of suggested maybe a different interpretation. Schrödinger, in fact, kind of one of the motivations was trying to find a smoothly evolving, flowing description of things. And he wanted to interpret his waves, Schrödinger waves, or wave functions, as physical waves, like water waves that evolved and flowed and did whatever. Heisenberg's matrix mechanics gave a different picture where there are these quantum jumps. If you read the paper, there's a lot of talk about quantum jumps and things. And that built off of language of Bohr and Bohr's atom, which was earlier. And so they would talk about, you know, an atom or an electron was here, and then it was here, and then it was never in between. So it just was a very different kind of notion of what's real. And in forming his theory, Heisenberg really heavily focused in on things which could be observable, and then basically kind of sort of a logical positivism, where things which were unmeasurable were not physically real. It's kind of it's a lot of that. So different kind of pictures of reality were emerging. After that, Heisenberg, you know, they quickly, Born and Jordan, zeroed in on the key kind of principle that Heisenberg was identifying was that x position momentum did not commute, and which meant that x times p was different than p times x. So there's a commutivity issue. So that came up whenever something behaved quantum mechanically. Commutivity came into play. Go along a little bit, and probably have the years all wrong. I think it's 27. Heisenberg wrote the uncertainty principle paper. I may have the years wrong.
Is it 26?
Is it 20, 26 was Schrödinger, I think. Anyways, it's all in the same. You know, it's all in the same thing. But it came after his matrix mechanics was done. Okay, I don't think I realized that one as a student. I kind of didn't have the flow of how things went. So, anyways, so Heisenberg wrote a paper, and he uses this picture of, he kind of really gives quantum mechanics a disturbance sort of interpretation, where you imagine, he talks about an electron moving along, you try to visualize, try to look at it with a microscope, and he shows that if you want to, in order for the light wave to be, if you use a long wavelength, to see the electron, you want to use a short wavelength light, but then it has interpreting it with Compton scattering, then it kind of violently shakes the electron, and so it disrupts the position. And if you try to use, weaker light, so it doesn't violently shake it, then you're not able to resolve and figure out where the electron was. And so you have this idea that, it really gives the idea that the electron has a position, but the act of measurement kind of disrupts it. And even though in other times that language isn't really what Bohr or Heisenberg would use. So they were kind of equivocating a little bit because, it's tricky and counterintuitive, and whenever you're doing something new, you're groping in the dark, okay? But and even now, and even I sometimes will kind of think about things with sort of like a disturbance picture of measurement. It has a position, but it was disturbed by the act of measurement. And so the question is then, is that right? Is that really what we need to have? And then in the Solvay conference, I think that definitely was, when you read through the Einstein-Bohr debates, a lot of the ways that Bohr was trying to analyze the various paradoxical situations suggested by Einstein was he was using this sort of disturbance picture to sort of show that quantum mechanics was consistent. Okay, so I think it's 35, but I don't remember. Anyway, so eventually Einstein got to the point where he was okay with the consistency of quantum mechanics. He no longer questioned that the results of quantum mechanics were consistent. A lot of the earlier arguments were about that. And so then he instead zeroed in on, yes, it seems to always work, and the mathematics is fine as far as that goes, but is it everything? Is it complete? And early on, it was very important to Heisenberg and Bohr and Pauli that for it all to hang together, it needed to be complete, so there wasn't any kind of other thing possible. And so the EPR paper, or the Einstein-Podolsky-Rosen paper, not to be confused with ER by themselves, Einstein and Rosen, they wrote a paper on the Einstein-Rosen bridge solution to general relativity, otherwise known as a wormhole. So same two of the three are the same. Anyways, the EPR paper is their attempt to suggest or to state why they felt like quantum mechanics, although consistent, could not be complete. All right. So I want to say there's a little bit, this is what, we'll go through what the paper says. Einstein, I think, was never happy with, so he wasn't involved with the detailed writing of it. He's I think he was there in the strategy phase, and so you have to know that, because later on, he didn't always phrase his objections quite in the same way. I think that we'll go with this. All right. So that's kind of the setting. And all right. So the EPR paper is looking for a problem in quantum mechanics, and they take a step back and they say, well, okay, what do we feel like has to be true? Whatever the rules are, they felt like it needs to be, and I would agree, needs to be compatible with relativity in some sense, whatever that means, but there's got to be some sort of way that you become or are consistent with relativity, either exactly or asymptotically as you zoom out. We now think exactly, but okay. Somehow you have to be compatible with relativity. Einstein didn't like the collapse postulate. So the idea that he definitely wanted to say that reality should be things that are real should be objectively real. They shouldn't need, so the famous example, he has a quote where he says, do you really think that the moon isn't there when you don't look? I'm paraphrasing, but that's the idea, that why should the position, the truth or the reality of the position of the moon have anything to do with me? Why should that be true? So, okay. So there are different ideas. On a lot of these philosophical issues, you can go to the Stanford University has the Plato webpage. It's through their philosophy department. And they have outstanding summaries on all of these philosophical issues with quantum mechanics. I mean, just they're really well written. So I would recommend looking at those if you're interested. Key ideas here. One would be the notion of separability. Okay, so whatever is going on in the universe, the idea is that I can do an experiment here and establish that something is real, a real experimental result, and I don't need to confirm or talk to anybody on the other side of the universe. I can establish reality with my local measurement. And so the idea is that local results are real and may be established without reference to somebody else, without external reference. Okay? It's kind of a picture of what they think has to be true. And they didn't really define, I don't even know if they quite used all these words. Some of these are things that, it's kind of vocabulary that's been developed to help people think about the paper. The paper is only 3-4 pages, maybe 4 pages long. It's really short, but you have to read it carefully. There's an idea of locality. And just think about this as relativity good. Okay, so the idea that really what you want to say is something like, what I do now cannot influence things on space-like separated places in space-time. We haven't talked about relativity, but the idea is if there are 2 points in the universe and they're so far apart, remember light travels at a finite speed and nothing can travel faster than that. So if 2 points are separated and there hasn't been enough time for light to kind of bounce, to transfer information, then they can't talk to each other. That's what we're really saying. So space-like separated events are independent, and what happens here cannot instantaneously affect what happens there. You have to wait. There has to be enough time, basically, for light to have carried, or something to carry the information. That's the idea. And this is kind of a tricky thing here. They have to define reality. No, that's too hard. But we don't get into philosophy too deeply, even though that's what this is all about, a little bit. So they don't define reality. That's too hard. But what they do is as a minimal, they define kind of a minimal condition for something to be considered an element of reality. And they say, if you can say an element of reality can be predicted with 100% probability or certainty. Okay, so you say, if you can predict with 100% certainty, then an attribute is an element of reality.
So it's only real if it could be 100% predicted.
No, that's a stronger
With 100%
statement.
certainty.
That's the statement they don't want to get to. They don't want to define reality. That's too hard. So they're saying, I don't know what reality is, but whatever it is, this has to be okay. They're trying to come up with a minimal condition, not necessary but not sufficient.
Seems like beating around the bush.
Yeah, yeah. And this is tricky, and Einstein didn't like this. In his later work, I haven't read all of his other stuff, but he did not use this. Okay? All right, but that's, yeah. When I say predict, I mean predict without in any way further interacting with it.
I just don't like how it says it's an element of reality when you haven't really defined what reality.
Well, you can't. I mean, how do you define? Okay.
I know
It's
you
the
can't.
question
I
of
still don't
isness.
like it.
Is it really true? All right. Is it really a property of something? You know, I think about this marker having a position. Like that's a real property of it. It's part of its essence. And the problem is that's what the whole question's about, right? And so they're saying, well, okay, if I can say 100% without doing anything else to it that something is true, then it must somehow be, there must be some sort of real isness about it. That's what they're trying to assert. I think I'm not going to agree with this. But that's okay. You know, it's all, yeah, I don't agree with this. But, okay. But they're definitely, what I want you to realize is I'm using the language, the classical language, where I'm talking about a system and properties of the system, not correlations with a possible measurement, right? And that's kind of the difference of what is going on here. So I'm using kind of classical terminology because that's what they used, right? And it's not that I don't agree with EPR's conclusion, but they parse the question, they kind of split the problem in a way that forces you to kind of see what the issue is. So even if I don't like the language they use, it's understanding why I don't like their language they use that helps me see, you know, what's going on. Okay. So the idea, okay, so the paper, so if you look on the web page, I photocopied the paper and I went through kind of line by line, I made annotated notes, and I went through and did the kind of math stuff. And I kind of got done and I realized, well, that's kind of beyond the level that we've been presenting things. Emily, I don't know, do you have that? You have the paper?
Mm-hmm.
I don't know, do you have the notes I made? Or not? No, okay. So in that same, on the webpage, I've got the notes too. They're like, they have my chicken scratches there. And so that'll help you if you try to read them. So, you know, and it's, okay.
Oh, this is on the website. It's not the paper.
Okay. So here's the idea. So there are mathematical technicalities and about forming. When you have finite dimensional spaces, it's all simple. When it's infinite dimensional spaces, getting the inner product to work, there's some technicalities about making things work, okay? And I think a lot of the early objections, people were quibbling about the technicalities, and that's missing the point. And in the notes that I've got here, I didn't go through any of the technicalities. In the other one, I kind of was getting more into technicalities. None of that matters. And so I'm going to pretend that the Hilbert space or the vector spaces are finite dimensional so that the technicalities aren't there. That's not really right, but okay. Then we're going to transition into the spin example where it all hangs together and you get the same issues. All right. So imagine so what they imagine is prepare two particles or two systems in states. So particle 1 goes one way and particle 2 goes the other way with momentum, say, P and minus P. Okay, how would you do that? Well, take a stick of dynamite. That's what they thought of that it would work. Stick of dynamite that just happens to split into two and only two pieces. One going one way, one going the other. The initial momentum was 0. Total momentum has to be 0 after the fact. Conservation momentum, fine. Okay, how would you describe said state? Well, you would say the total system is in a state, and I wrote them, but I'll say minus p, p, 1 and 2. Okay? All right, fine. So imagine these things scattered far, 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 far away, such that they are space-like separated. Okay? So, and once they're separated, they become space-like separated, but I'm saying let's make them extremely separated so that there's, so that basically it would take, an hour or something to send a message back and forth between them. Okay, that's kind of to make it really clean. All right, so the idea would be, so person 1, my name's person 1, and over here, I'm going to have person 2. Okay. So the idea is going to be, all right, now, all we know beforehand was that it was prepared in a state of 0 total momentum. We don't know the momentum of either bit, we just know the total momentum was 0. So person 1, beforehand, and person 2 also, they don't know what momentum in the little fragments will have. What they know is that whatever one has, the other has. So I wrote it like this, but in fact, because they don't really know the momentum, what you really should do would be take a superposition over all of them. And so I'm going to pretend it's finite dimensional. This is where all the mathematical stuff comes into this. You'd say there's some coefficient, some weighting, right? So you would weight all the possible states like that, okay? And so person 1 doesn't know what they're going to find. They could find any or all of these momenta with some relative probability, as we've talked about today. And person 2 would find the opposite momentum, whatever it is, with corresponding probability. Okay. All right. So, okay, so let's assume then that person 1, so before making a measurement, they couldn't say what happens at point 2, but so this could be Earth and that could be Jupiter. But let's say you do the experiment and person 1 measures specific value, person 1 sees minus p. Okay? Okay. Now, think of the system in totality. After this person measures momentum, the wave function collapses. And what's the state after which?
Should be minus p.
Yeah. So this system on the tensor product space, or the total system, collapses to this. So you measure p. That's what you get. Okay. All right. Okay. So here's the thing. Person 1's on Earth, person 2's on Jupiter. They're space-like separated. So the assumptions we want to make mean that whatever person 1 does can't do anything to affect what's happening on Jupiter.
But since they say he's made.
And yet, yeah. So that means that because the person 1 can't influence the outcome of an experiment on Jupiter, it must have had that momentum all the time. Even though it wasn't known, we didn't know it had that momentum, but it must have had that momentum.
And that's just entanglement, right?
Well, okay, so the fact that these are entanglement means that the information intertwines pieces which are separated. So the fact that these are coupled like this means they're entangled. so the information between what happens here and there are coupled. That's entanglement. So Einstein, Podolsky, and Rosen say, okay, the fact that you could establish the momentum of something and your space like separated, it means that it must have had that before you measured it. And then they would say, oh, okay, so person 2 could measure momentum, in which case they would find P with 100% probability. So it was an element of reality. But if they chose to measure position, they get something else. They get a number. You measure position, you're going to find an answer. It may be completely, your ability, you may not be able to predict what you'll find, but you will find something after measurement, upon measurement. So then what they would say is, okay, well, momentum was an element of real. So momentum must have been real. And because you could predict it with 100% probability. On the other hand, you could also measure, if you chose to measure x instead. And so it must have been, and so then after you measure it, it's real. Well, then it must have been that position and momentum were both real properties of reality, even if you couldn't predict them or know about them. But they must have been real before measurement. Okay, because there's, all right, so that's kind of the basic idea. And you can, well, I don't know. Okay. So that's kind of their argument. What they would say then that quantum mechanics, they don't quibble that the math is consistent with itself and that it predicts what we see in experiments, but they would zero in and say, evidently there are elements, there are bits of reality which are not encoded in quantum mechanics. Such things are often called hidden variables. There must be, and then what you would do is want to interpret quantum mechanics, the probabilities in quantum mechanics then would not be probabilities of, irreducible probabilities. You would instead want to say that they are probabilities of ignorance of whatever this hidden stuff that we somehow couldn't get access to. That would be the way to say it. Is that okay? There are all sorts of things you can think about. So Bohr, probably putting words in his mouth. Bohr, and when I say Bohr, I really mean the Copenhagen kind of family of people. So that'd be Bohr, Heisenberg, Dirac, Pauli, Jordan, Born, that whole group. They would say no, okay? They would say no. They would say, well, okay, I'm kind of smearing things. So remember I said that Bohr and Heisenberg were using this sort of disturbance model to account for experiments. They really were thinking about the particle having a momentum, moving around. Sometimes when they did little back of the envelope calculations just to kind of get the essence of the idea, the actual math didn't have that, but okay. It didn't need that interpretation, but okay. And then in order to answer this, I think it kind of forced them to really fully kind of buy into the idea that no, in order for, they instead want, if quantum mechanics is to turn it around, if it is to be complete, then evidently this picture of a particle carrying a property with it is wrong, and that that isn't real. And so then the picture that they develop, and I'm not quite clear on the timeline on some of this, but a lot of it, I think what happened was that after EPR, they kind of had to really bite the bullet and just carry things to their logical conclusion is really the issue. And so then you would, the picture that emerges is that, oh, okay, no, what they would say is what's real are the correlations between things, that that the particle has no particular momentum or position or anything until it is an observed property, and the act of measurement kind of forces the particle to make a stand, and that's at the point where you can assert that you can, when it's up, that's when it becomes 100% correlated with something, and then what that means then is that if it's the correlations which are real, it means that there's sort of a subtle, there really is a subtle non-locality in all this, and that actions at person one are changing the wave function you would assign for the whole system. So the actions of person one really are changing the wave function describing the universe, which means it somehow reaches out across all the way to Jupiter, but it's sort of a perverse sort of non-locality, because there's no measurement a person at two can perform locally, which tells them that person one made that measurement. So there's a non-local character to things, but it's sort of a subtle one. It's sort of a slight non-locality in that there's no way, what we would say now, is there's no way to signal with it. So person one makes a measurement, but there's no way that person two could locally make a measurement to know that person one made a measurement, the results of that measurement, or even if they made a measurement at all. Because all person two has a choice of is measure position or momentum, and they get some result. They have to choose one or the other. They can't choose both. And they don't have any way of knowing about the result of the unperformed measurement. So they don't know. They measure position. They can no longer say what will happen for momentum. And so, okay, so you got these two pictures of reality now. Sort of this local realism is what it's called. This Einstein picture is local realism, where the reality is kind of carried, like every particle has a suitcase, and it carries its reality with it, and or not. And the Copenhagen picture is that no, there is no local realism. And when you read them, they talk about that nature is not visualizable, that you can't think that reality is not visualizable. You can't think about particles as moving around, having positions, unless you measure them to have a position. Right? The only thing you can assert is real are the results of experiments. Okay. So to get away from kind of this sum, making that precise is mathematically a little touchy, and I've avoided it thus far, and I'm going to keep avoiding it. So instead, we're going to recast this. Bohm came up with a spin version of this, which I alluded to, where instead of saying, you say this is like, let's say, what you do instead is you have a state of zero spin or momentum, angular momentum.
So the same anti-correlated one.
Yeah. So what you get is a situation where you don't know the spin of either one, but you know that they have to be opposite. So you get states, basically you prepare the system in A plus or minus Z. So it's going to be 1 over root 2, equally correlated with each outcome, but it'd be plus Z for 1, minus Z for 2, minus Z plus Z. Okay, and then again, equal and opposite, you sum over them, but it's nice because there are only two possibilities. All this stuff about convergence and mumbling about mathematical technicalities, wave packets and all that, doesn't matter because it's a finite dimensional space. It just works the way, but it works the same way. The idea then would be you just recast everything. You recast it to say, Einstein would say, instead of saying, basically he would say, you can, if this person one can establish that person two will always get minus z, and they're space like separated, then it must have been minus z the whole time, because there's no way you can kind of dynamically influence what happens at two. And so the spin of the particle two must have been minus z, say, the whole time, or plus z, whatever it was the whole time, regardless of measurement. And again, Copenhagen would say, no, 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 the spin at two was nothing, or was not a specific anything. It just had potential values, not realized values, until person one made a measurement. And then the wave function would collapse, and there is this non-locality, such that after person one measures it, the state of particle two is, let's say this person measures spin and finds plus z, so it collapses onto this factor, and then the state of particle two would then be definitely minus z. But it's kind of perverse, because even though that's all happened, person two doesn't even know that that's true. They just perform their measurement, and they always, of course, they always get minus z, but they can't tell if that happened because it had to be, or just it was 50-50 and they just happened to get whatever they got. It's only upon later coming together and comparing results that person two says, hey, oh, I see that every time you measured a plus z, I got a minus z. But in the moment, they have no way of knowing. Yeah. All right. Okay, so I'm trying to hit all my points here. So Schrodinger's the one who, I think he used the German word for like intertwined, but it got translated as entangled. So these states, these represent entangled states where the correlations are between kind of separated systems. Okay. So at this point, so that's the EPR paradox, and I think I've tried to phrase the two different perspectives, and I think it basically just sat there. Bohr kind of wrote this paper. If you try to read it, it's jumbled. It's not always clear what he meant.
There were a lot of Bohr's papers like that.
Yeah, I mean,
all over the place.
he had this gift of writing these paragraphs, and then when you look at it, it's like, holy crap, it was one sentence. It's just like clause and subclause on the subclause, and it's like, you get lost in it. But basically, it you know, like many things, when you don't have experimental results, they devolve into kind of religious statements where people believe one line of thought one thing, and saw this as confirmation of their thoughts, and people thought differently, saw it as confirmation of their thoughts, and the two beliefs are not compatible, and you can't tell which is which, and you just have to make a choice. It wasn't until Bell thought about it, and he actually found that there was a way to start to decide between them. Okay. So I will stop this video here.